Okay, everyone, it's 10 past 12. Time for the next talk, the third and final talk of this session before lunch. I'd like to introduce you to Christine Spang, going to tell us about FFI and why you should use FFI rather than subprocess. Thank you, Christine.
Hi, everybody. I'm Christine. Hi. First things first, I want to thank you all for being here in this room. I've been a part of the Python community for a number of years, but this is my first time on stage, and I'm really, really excited to give back to a community that I really, really love. So before I jump into my material here today, just a tiny little bit about me. I got my start in the Python community in Boston after I graduated from MIT. In Boston, I was a co-founder of the Boston Python Workshop, and I was involved in the Python user group there, and also used Python in my work at a company called Ksplice. And now I moved to San Francisco and started a company called Inbox. If you want to learn more about Inbox, you can talk to me later, but that's not what this talk is about. At Inbox and in my personal hacking, we love Python. We're using Python for everything. Python's a really great language for figuring out what you want to write and writing it quickly. So this talk is about the times when you're writing Python, but you have some other code that you want to run that's not Python. Sometimes there's not a library available to do what you want, or sometimes it's not fast enough. Sometimes you just want to be able to quickly shell out to some code that already exists. So we're going to talk about these two different paths to running external code via Python. The first one is running an external binary from Python, and the second one will be wrapping a C library from Python. And so this kind of stuff, this systems level stuff, is very platform dependent. So I want to get it out there from the get-go that I'm talking about CPython, and I'm talking about Python 2.7, and I'm also talking about Linux. So there will be a few details that are specific to these particular platforms. But the general principles definitely are cross-platform. You just need to figure out the exact details that have to do with your platform. All right, the first part of the talk, why you shouldn't shell out, and sometimes why you should. So say so at work, I'm building an email platform, and email consists of text, and it turns out that text is written in every single language out there. And especially email, there are lots of different ways to represent that text to a computer. And these are called character encodings. And it turns out that Python only supports a subset of all the character encodings out there, out of the box. I suspect this is for portability reasons. It has its own implementations of character encoders. But it doesn't support everything. And if you want to build some software that is able to handle email from everywhere in the world, all sorts of crazy spam, stuff like that, you need to support all of them. So I ran into this problem where I wanted to be able to decode text that Python didn't support. So the first idea we had here was to use this program called iconv, which is pretty much the standard way, the standard library for dealing with text conversions on Linux platforms. And there's a command line program called iconv that you can use on the command line and use it to convert text from one encoding to another. So if we want to use this program, we can write a little script in Python. Say we'll call it convert UTF-8, and it might look like this. So you see here, super simple. There's really only one line here that's actually doing anything interesting. So we're parsing some command line arguments, and then there's one line right at the bottom here. It says subprocess.checkCall. And then we see our iconv command line program and all the arguments that you would send to that on the command line. So this is an example of shelling out. And by shelling out, I don't mean using a shell, actually. There's not necessarily a command line shell involved here. though there are some arguments to the subprocess module that can make you pass your command through a shell first. I'm just talking about running this external program from Python. And this would obviously usually be part of a bigger system, but I've just cut down the example here to make it really simple. All right, so what's actually happening here? This is one line of code, but it turns out there's a lot that's happening behind the scenes. And we want to find out what's going on. So the first thing I might do when trying to figure out what's happening in a particular line of Python code is use the documentation. So Python has these great introspection capabilities, so I could just call help on the function. And I've shown right here what exactly is the help string for check call. And if we can take a look at it, and we see it says, run command with arguments, wait for command to complete. OK, so it doesn't really tell us what's going on. It does tell us how to use it, which is great. That's all we really need to know. But I want to know more. And in the case that I want to know more, I want to know exactly what's happening with a piece of Python code. What I'm going to do is I'm going to read the source. So since Python's open source, I can just take a look at the source code for it. So let's do that right now. So yeah, hang on. Here we go. Just pointing out one thing. If you want to find the source code for any particular Python module, there's a Python standard library module called inspect that will help you with this. So you might have used like the dunder file attribute of a module. An easier way is to use the inspect module because dunder file, it doesn't necessarily always have the right thing in it that you want. And it also will show you the compiled Python file and not the source file. So you can import this function, get source file, and then you can call that on your module. And it'll tell you where the source code is. So we can pull up the source code like this. So I have IPython here. I'm going to pull up this file. All right, and I'm going to edit it. This is a little bit too big here. Let's make it a little smaller. All right. So I'm source diving. I want to find out what's happening here. So the first thing I do is so the call that we wanted is called check call. So we can search for that. All right. And then we just kind of follow the call chain down until we find out where the actual work is happening. So we can see that this calls another function called call, and then it does some stuff with the return code to wrap it properly. So actually calls right here on this class is wrapping this popen class, so we can look at that. And then it turns out if you follow this call chain down far enough, you get to a place where it calls this line of code os.fork. And if you look at the documentation for os.fork, this is a wrapper for the fork system call on your system. All right, so what's actually happening there? What's a system call? So a system call is the interface between a user space application, such as this little script, convert UTF-8, and the operating system of the machine that you're running on, such as Linux. So let's talk a little bit about the fork system call and what it does. So if we want to learn more about a system call, we can use a man page to read about it. So every Linux system should come with a full set of man pages for the system calls in the Linux Programmer's Manual. So if we take a look at the fork system call man page, it gives us a lot of information about what's happening here. So it tells us that fork works by duplicating the process that's calling fork. So when we do this subprocess call, we're actually duplicating our Python process. Oh, that's interesting. All right, so let's look a little bit at a visual representation of what is actually happening when we call fork here. There's a few other system calls involved when we're doing this subprocess call. So what happens is the Python interpreter calls fork. It splits into two processes. One is the parent and one is the child. The parent ends up sitting around waiting for the child. So there's this system called waitpid. The child actually runs this other system called exec. And that loads this other program, iconv, into memory and then runs it. All right, so a few more details about fork. So I said that the Python interpreter copies itself. The operating system copies the Python interpreter when you call fork. This would be really, really expensive if there weren't a specific way that this happened that made it so it didn't take so long. So when you copy a process, you have to create an entire copy of the memory stack. But if we created a copy of every single piece of memory that belonged to that process, it would take a long time and it would also use a lot of memory. So it turns out that the Linux kernel implements this fork system call by making the new process use the memory of the old process in a way called copy on write. So that means that it only copies the pages if the new process ends up writing to those pages or changing them. So that way it's a lot faster, but it still has all this overhead of using the operating system. Whenever we ask for something from the operating system, the computer has to do this thing called a context switch. Switches into like the kernel mode and does stuff for the program, and then it switches back. And in the case of doing a fork, we then have two processes that the Linux kernel then has to schedule between. So to illustrate a little bit more about this copy on write thing, I've showed a little excerpt of a top command running a Python program that I loaded a lot of stuff into memory and then I forked. And then I captured it on top. And you can see here that the amount of memory being used by those two processes is more than is actually available on this particular machine. And it's not using, if you've heard of swap space, there's no swap space being used on this machine right now, so it's not swap that's taking up that slack. It just so happens that this tool top doesn't really know about copy on write, and it just thinks that that memory is being used. So in order to be able to do this fork thing, the Linux kernel has to have a certain way of like looking at memory allocation. So the Linux kernel pretty much has to assume that a process could possibly unshare all of its pages after it does a fork. So it has this feature that I'm going to talk about a little bit that allows it to kind of like assume that it's going to be okay. And to illustrate how that works, I'm going to compare this to how so the Linux kernel, its memory allocator, it treats memory allocation a bit like how airports or airlines treat selling tickets for flights. So the goal of an airline is to maximize their profit by having their flights be as full as possible. And so they do this by actually selling more tickets than there are seats on the flight. Because it turns out that most of the time, some passengers don't show up, but you still want to have a full flight. So you sell a few too many tickets, and then some people don't show up, and then you hope that it works out just so that the amount of people that don't show up are about as many tickets as you oversold. And of course, you can do models to make sure you like get approximately the right amount, and usually it works out okay. And so the Linux kernel basically does the same thing with memory. It has this feature called overcommit, in which it turns out that most user space processes also ask for more memory than they end up using. So it will allow people to request more memory than they actually than actually is available. And this is what allows the Linux kernel to be like, okay, you can fork, it's copy and write, but you might unshare everything, but it's okay. So just a little more about overcommit. You can actually tweak these settings on the kernel. You can like change how it actually allocates or responds to requests. If you disable overcommit, fork, if it will take up more memory, if copying the entire process would take up more memory than is available on the machine, it will just fail. And this can get a bit more complicated if you start involving virtualization and containers. Sometimes you'll run into situations where the Linux kernel actually does give out too much memory, and the equivalent to the airline giving people vouchers for taking a different flight is actually this thing called the killer, in which it uses this algorithm to just pick random processes to kill. And that's not really a good situation. But the point that I'm trying to get across here is mostly that there's a lot of things going on under the hood. When you call it subprocess, you can run into weird failure modes depending on what your setup is. And also there's a lot of overhead in that it has to ask for a lot of things from the underlying operating system. So you can run into problems there. But there are also like a lot of reasons to use subprocess. And it turns out that most of the time I do use like shelling out a lot. It's really simple. If there's just a command line program that you have that you want to run from a Python script, I would just shell out. It's super easy, and most of the time it works. And it's pretty flexible, flexible enough in most cases. You can like read the standard out and the standard error, and you can communicate via pipes. And Python's wrappers will throw Python exceptions. So you don't have to deal with return codes really. But there's these dangers. I talked about the overhead. Also, it is the case that it's a limited API if you're just going to communicate over the command line. And also, if you have to transfer a lot of data to this program, you run into buffering issues. If you have to, you'll have overhead from I/O if you are writing out temporary files because you can't just transfer data in memory to the process. And if you're using a bidirectional pipe, like if you're like sending information to the process and getting information back, you can run into deadlocking issues. So it can get a little complicated. And I would say that if you're trying to do something more than the simple just like run it and look at the standard out or standard error, you probably don't actually want to be shelling out. All right, so do it anyway usually. I do it all the time. But now we're going to talk about a different case. So there are a lot of times when shelling out to a process is not good enough. And those cases are usually when you care a lot about performance, like you're going to be invoking that program a lot of times, or just like you need a more flexible interface. A command line program just doesn't have enough, it doesn't allow you to just invoke a single function. So how do we do that? How do we call C code from Python? So this involves something called a foreign function interface. And a foreign function interface is just a way that programming language translates between the calling conventions of one language and the other, and wraps like the data structures and makes them available. So there are a bunch of different options for calling C code from Python, and I hope to shine a little bit of light on the landscape here. So the first option is to write a C extension. So Python is just, or CPython at least, is just a C program. And you can make more code available from Python by just writing more of the same code. So write more CPython, and then you have more Python available. You end up writing a lot of C that way, and you use Python's C API. So you can use C types, which is part of the Python standard library. It wraps this other library called libFFI. You don't need a C compiler. You can just load the module right into memory. And it's a bit tedious. It's kind of clunky. It has a few drawbacks. There's this thing called Cython, which is kind of like a hybrid language between Python and C. And I think people use it more for like optimizing speed than just like accessing external libraries, or just like I have this one little function that's kind of slow, so I'm going to write it in Cython and use that. And then the option that I'm going to talk about a bit more is called CFFI. This was written by the PyPy authors to address some C-type shortcomings. You can use it at the API or ABI level, so you can write it against like the C, the API that the C library provides, or you can do the ABI, so like the compiled version, which is less flexible and like a bit more brittle, but you don't have to use a compiler, which is kind of nice. All right, so I want to talk a little bit more about these different options in the context of a problem that I had at work, which we talked about before. So in order to like get around this, like, oh, I have to like shell out every time I want to convert some text from these weird encodings, we looked at wrapping this library that iconv provides called libiconv. And it turns out that the command line program iconv is just a command line wrapper to this library. So it turns out there's a library called libiconv that's available on PyPI that implements a C extension module for Python. And it looks a bit like this. And I can show you a bit more about it. Go, Tmux, go. All right, here it is. So you can see it's like about 250 lines of C, and it looks like C. And this right here is kind of the meat of it. There's like 3 API functions that libiconv provides. It's super simple. They're called iconv open, iconv, and iconv close. So the main one is called iconv, which does the actual conversion. And you can see this wrapper here. Writing C code can be a bit tedious. So you notice that there's like, I've shown you like a page of code here, and it's actually just still parsing the arguments to this function. So definitely a lot less concise than Python, and not really doing anything here that involves actually interfacing with the library yet. So none of this is really interesting until we get to here, where we actually are performing the conversion. And I actually read a lot of this code when I was thinking about rewriting it, and it does like a few questionable things. It has a few bugs that I wanted to fix, but I kind of decided that the whole approach that they were taking was not very good after all, in that it like converts things to like UTF-16 and then dumps that directly into Python's internal Unicode representation via the Python C API, and like that's actually dependent on like the platform you're on. So I'm a little surprised it actually works, but it probably means that I'm just running it on the same platform as the person who wrote it. So there are a couple reasons that I wanted to improve this, but kind of decided that I didn't actually want to use it after all. All right. So I decided to write a different implementation using CFFI, which I'd heard was pretty much the best option for shelling out to an external library from Python right now. And I'm going to show you a bit about the implementation that I wrote. So this is an excerpt, which is actually the interesting part, but I'm going to pull it up on a terminal so we can look at some more. Gosh, this is too big. All right. So that's the whole thing. You probably can't read a lot of it, but I'll tell you a little bit about some things. So this whole file ends up being 150 lines, and I have actually a lot of documentation in here. So I'll tell you a little bit about how CFFI works. So it's pretty simple to set up, and you have like a little boilerplate here where you have to like get a handle on this FFI class. And then you got to tell CFFI a little bit about the C code that you're wrapping, just so it knows how to like set up the mapping from C to Python. So here I'm just like giving some declarations, but I can actually I can leave a few things out here. So I tell it that there's some constants that I want to use, but I don't have to tell it what the value of the constants are, because it turns out that CFFI can figure that out on its own. And I say there's like some C structs that I want to use, but I don't have to tell it the size of the struct or what the individual members are, because CFFI can also figure that out, which is pretty sweet. And then you run this verify call, which is what in development, CFFI will actually transparently invoke your compiler behind the scenes, which is really sweet. You end up not having to go through the typical C workflow of edit your code, invoke make, or like manually compile, and then check and see if it works by running it. So CFFI for development just does that behind the scenes for you, which is a really magical experience, honestly. Yeah, so this verify step is just what CFFI does for like figuring out what are the sizes of these things and setting up the mapping to Python. And so a lot of the rest of this file actually ends up being Python. One of the amazing things about using a library like CFFI is that you end up being able to use C code, but also use Python mechanisms for abstraction. So right here, I'm writing a class. I'm calling it iconv, and I'm giving it methods. And I implement it as a context manager, so I can use the with statement with it, and have it automatically call iconv close when it's done. So it's really nice to be able to use the better abstraction mechanisms that Python provides, and to not have to write all of my code in a typical C fashion. All right, so let's look a little bit about the interesting part here. So the interesting part of this code is this one method iconv, and a lot of the work here is actually just allocating a bunch of C data structures from Python, which is really cool. So I can call FFI.new here and pass it a character pointer, and wow, I've allocated a piece of memory and I have a handle to it in Python. And then CFFI handles a bunch of things behind the scenes kind of magically, in that you can use a Python string and assign it to a character array, a C character array, and it will do the right thing. And it has a bunch of different other different features. A lot of this is just setting up the proper pointers and strings and byte arrays. And then I have this one call here where I call the iconv C function from Python, and then I actually cast it to an integer. And that's the interesting part here. It's about 40 lines of code that actually interfaces with C, which is definitely a far cry from the 250 lines that we saw in the Python extension. So you can see that if you go from, this is not a complete, a totally production-ready version yet. I have to fix a few bugs and also package it properly. It's just a single development file right now. But in the general case, you end up writing a ton less C if you're using something like CFFI instead of writing a C extension. And that's really great because it means C is really awesome, and it allows you to be really close to the machine and feel like a wizard and do a lot of things that you can't do from Python. But that doesn't mean that we want to be writing C all the time. I don't want to be spending pages of code parsing arguments or dealing with a lot of different string things. So if I can make the amount of C that I write just the amount that I need to interface with this library and do kind of the interesting C things that the library provides, my life is going to be a lot easier. I'm going to spend a lot less time maintaining things. It's going to be faster to write and also easier to debug. So the conclusion of this little section is to write less C for all those reasons that I just mentioned. A little summary, the Python C extension that we looked at, 250 lines of C, CFFI wrapper, 120 lines of Python in C. Around 40 of those actually interface with C. All right, so let's take a look at everything that we talked about here. What did we learn? First, we talked about calling external processes from Subprocess. And this is the really simple way to do things. But it has a few caveats. One is that it's really expensive. It can do crazy things with memory. It can take a lot of computation time because of the context switches between user space and kernel space. And it's a little inflexible. So if that's not going to be sufficient for your needs, you might want to look at wrapping a C library. And we showed you that one example from this problem that I was having, in which I reduced the amount of C that, or rather, I showed you some options. And you can write a C extension. You can use C types, just a little clunky, or you can use CFFI. And using CFFI allows you to minimize the amount of C that you're writing. And there's obviously cases where you're not gonna, where some other option is gonna be better. There's tons of different wrappers out there. Like if you're using C++, you might wanna use like Boost Python or something like that. But if you, for the simple case where you're wrapping a C library, I think CFFI is a really great option. And so we talked a bit about a lot of like systems level things that to think about when you're writing code. And I really want to highlight here that even though most of the time we spend writing a high level language like Python, a high level language means that there's a lot of levels underneath your level. And all of those different pieces affect what you're doing. So you need to understand them sometimes. Most of the time, you can not think about them because things just work, but when things go wrong, you still need to understand the pieces that are underneath Python. So it pays to learn those pieces, learn things about your operating system and the interface between Python and your operating system. It'll really pay off when you have to be optimizing things for speed, when you have to be debugging weird errors, when you have to be running systems in production. And that's all I have for you today. Thanks so much for coming. Say hi to me. You can follow me on Twitter. All the code that I showed you today is on GitHub, so github.com/spang. If you have any questions about C or subprocesses or systems or inbox, ask away. I'll be here. I guess lunch is up next, so I can hang around for a few minutes afterwards. It's no problem.
Plenty of time for questions. If anybody wants to use the microphone, that aisle and the other side aisle.
So when you were writing the CFFI code, how did you debug seg faults?
There's a lot of ways. You can still print things from using CFFI as well. You just kind of do printf from Python. There were a few things that I had to deal with in that dealing with like text processing from Python. There's often sometimes where you cast something to the wrong type and like I get like some crazy output, or like I was giving it a pointer to the wrong data structure and it would just crash. But it's pretty much the same as C, except for it's nicer because CFFI does the compile step for you, which is pretty sweet. Thanks.
Hi, do you have any suggestions on resources for learning more about the layers between Python and everything under Python?
Yeah, sure. For Linux, there's a great book called the Linux Programming Interface, TLDP. It's a really good book. You should check it out. I don't have anything else that I can think of off the top of my head, but I can think about it a bit and like write something up. Cool.
Is using C types is it a lot more complicated than CFFI?
I haven't done it personally because everything that I read said that CFFI would be easier, and I use it and it worked. So I've heard that it's kind of clunky and you have to write more code, and there's some problems with it. I don't know specifics though. Yeah, over there.
It seems like CFFI might be a decent sort of bridge step to someone who with experience writing Python, wanting to learn more about writing C. But I could also see how that might not be the case. I was just wondering what your opinion is.
I think if you're like a very beginner, you probably want to start just writing C, actually.
Yeah. Okay.
Just there's fewer moving parts, so fewer things to go wrong. If you're just writing a C file and compiling it. And you want to know about that stuff anyway, because if something goes wrong with CFFI, then you don't know what's going on. Cool. Can we get the other mic actually?
Hi, thanks for the talk. It was great. I have
welcome.
a question. Do you know if this library supports Jython, so Java libraries calls?
I don't think it does. It supports PyPy, but it's obviously dependent on the back end.
Okay.
Thank you.
Hi.
Over here?
Have you tried Swig, or is there Is there any reason you didn't use Swig? Because it would look like a out-of-the-box kind of easy solution for C, especially.
I didn't use Swig. My understanding of Swig is it does some sort of like code generation, and like the kind of automatic stuff that CFFI does was really appealing to me. But there's like a lot of options, so the reason that I haven't tried all of them is mostly that there's a lot of options.
Okay, thanks.
Anyone else?
Looks like that's it for questions, so thank you, Christine. I hereby declare it lunchtime.